All right, so we're going to continue with lesson 1 of unit 4. In our previous video, we looked at the relationship between a function, its derivative, and its second derivative. And we did that in terms of a graph, or the graphs of those three. And today we're going to actually focus on functions and their derivatives and the information that we can gain from them from an algebraic perspective. So our first example that I want to start with is the one that's in your notes, and that is f of x equals x to the third minus 12x minus 5. Okay, so in all the things that we want to find, if you're following along in the notes, we're going to need the first derivative and the second derivative. And so the first derivative, f prime, is going to equal 3x squared minus 12. And the second derivative, and I'm going to change colors, that one's about to run out. So f double prime, the second derivative, will equal 6x. Okay, so we know we're going to need the first derivative and the second derivative, and we're going to use information from the first derivative and the second derivative to help us find information about the characteristic or the characteristics of the behavior of the original cubic function. Right now, really the only thing we probably can look at and tell really quickly is that this is a cubic function, and we know that the cubic function should look, something like this. Okay? So what I want us to do is we're going to what we're going to do is we're going to figure out, okay, just exactly on what interval does this function increase, decrease, increase again, and then I also want to know where is the local maximum and local minimum. And all of that information we can identify from the information for the first derivative and the second derivative. Okay? All right, so let's talk about finding the critical values of the function's derivative. That means set this derivative equal to 0 and find the zeros. So I'm going to add 12, divide by 3, and I get x equals plus or minus 2. So these are the critical values. Okay, these are the critical values. And I'm going to take those critical values and I'm going to put them or create a little sign chart. Actually, I want that to be green. Okay, and so I'm going to use these two critical values to help me determine information about the original function. But let's first talk about this. What do we know about the derivative? Well, you know that this derivative is a quadratic and it opens upward. So, we know that part. But let's just talk about it a little bit more specific. Since we found the zeros of the quadratic, we know that the derivative has x-intercepts at -2 and +2. What I want to know, what I want to determine from the derivative is if I look at x equals -2, everything to the left of -2, the graph of the derivative is above the y-axis. And when the graph of the derivative is above the y-axis, that means that the y values of the derivative are all positive. From -2 to +2, notice that the derivative is below the x-axis, which means the y values of the derivative are negative. And then at 2, the graph of the derivative goes back to being positive, which means the y values of the derivative are positive. Okay? Now, by identifying that, I now can determine quite a bit of information about the original function. So, my critical values are at -2 and 2. From the derivative, wherever the derivative is positive, the original function is increasing. So that means f is increasing, is increasing on -infinity to -2. The original function is also increasing on the interval 2 to infinity. And the reason is because f prime is greater than 0 on those intervals, period. Now, the derivative also tells me that f, this function, is decreasing on the interval -2 to +2. The reason? Because f prime is less than 0. So on your notes that you're following, the very first page gave you all of these scenarios, and we kind of talked about this when we looked at the very first video, when we were looking at the graphs of a function and its derivative and its second derivative. Okay, so let's identify where f has a maximum. Okay, well, f is going to have a maximum where the derivative changes from positive to negative. The original function will have a maximum. Well, I want to know the actual point where that maximum is going to occur. So now I'm going to substitute -2, where I know the x value will have a maximum. Substitute that into the original function, -2 cubed minus 12 times -2 minus 5. And this will be, what is that? -8 plus 24 minus 5. And this is -8 plus 24. That's positive 16. And 16 minus 5 is 11. So I'm going to have, or f will have a maximum at the point -2, 11. I know that the original function f will have a minimum at x equals 2 because the derivative changes from negative to positive. So now f of 2, I will take my 2 and I'll substitute it in for x into the original function. So I have 2 cubed minus 12 times 2 minus 5. And this will give me 8 minus 24 minus 5. 8 minus 24, what is that? -16. And -16 minus 5 is -21. So I have a, or f, not I, but f has a, and really I should say local minimum or relative minimum at 2, -21. Now, just so I can reiterate this, a local minimum and a local maximum indicate where a function changes directions, okay? So I know that -2, the original function f is going to have a local maximum at -2, 11, which means it's going to change directions at -2, 11, and f will have a local minimum at 2, -21, okay? All right, so now let's talk about the second derivative. I want to set the second derivative equal to 0, I'll even scoot that over here a little bit. And let's talk about x equals 0. So this x equals 0 is a hypercritical value. And hypercritical values come from the second derivative. Okay? Well, let's think about what the second derivative's function is. The second derivative is simply a linear function. What would that linear function look like? It would look something like that. Sorry, I'm off the page. I apologize for that. Okay, so let's talk about this. Everything less than 0, everything to the left of 0, the y values of this function are negative. All the y values to the right of 0 on this portion of the graph they are positive. So at x equals 0, the second derivative changes from being negative to positive. And so that is some information that we have determined about the second derivative. Well, what information does the second derivative give us with regards to the original function? Well, wherever the second derivative is negative, the original function is concave down. Where the second derivative is positive, the first derivative is concave up. Okay, x equals 0, because there is a change in concavity, this is going to be a PI also, a point of inflection. So, for a point of inflection, the PI, I will substitute 0 into the original function. F of 0 equals 0 cubed minus 12 times 0. Scoot over. Minus 5. And I get an ordered pair of 0, negative 5. And so F has a point of inflection, or an inflection point, at 0, negative 5. All right, the other piece, I can finish out the description. F is concave down on the interval negative infinity to 0, because F double prime is less than 0, and F is concave up on the interval 0 to infinity, because F double prime is greater than 0. So now that we've kind of identified all of that, let's really see what that gives us in terms of the original function. So if I were to take my information and plot, or just kind of sketch the graph of this information here, I will get a pretty decent idea of how this behaves. Okay, so here's what I'm going to do. Let's identify the local maximum and the local minimum. So my local maximum is going to occur at negative 2, 11, so up here somewhere. So negative 2, 11. My local minimum, which means the graph has to do that, my local minimum is going to occur at 2, negative 21, so over 2 and down to 21-ish, so 2, negative 21. Because it's a local minimum, we know that it has to change directions, and it has to change from decreasing to increasing. So let's talk about another point. So we've taken care of this, we've taken care of this. let's talk about this 0, -5. So 0, -5, this little point, let's say that's 0, -5. This is the point where our original graph, our original function's graph, is going to change concavity. We're going to have a change in concavity here. So, we know that on -infinity to 0, this portion right here, everything up to this point, the original function is going to be concave down. So what does that look like? So here I've got, am I still on the page? Yep. So concave down, and then at 0, we have a point of inflection, which means this graph is going to change from being concave down to concave up. Now, a lot of times it's very, very subtle, and especially the way I'm drawing it, but from 0 to infinity, the graph of the original function will be concave up. So, concave down, concave up. So we've addressed this, and the concavity. Let's just go back up here and verify that f is increasing from -infinity to -2. So it's increasing from -infinity to -2. I'm going to drop down to decreasing. It decreases from -2 to +2. Then at +2, the graph begins to increase again, and it continues increasing in from 2 to infinity. Now, there we have a much better idea of what this graph looks like, and what we used was information about its derivative and its second derivative to find that information. The other piece of information that might have been helpful is these pieces of information here, those x-intercepts. Well, how do you find x-intercepts? Remember, x-intercepts come from where f of x equals 0. And x cubed minus 12x minus 5, if I were to set that equal to 0, then at this point I would need a calculator to be able to find that, because this x to the third minus 12x minus 5 does not have nice intercepts, and they would be difficult to solve algebraically. Okay? Okay, let's look at another example. Let me change pieces of paper here. Okay, so now let's take a look at a trig function. So let me pull this down a bit. All right, so let's say I have f of x equals sine of x. And I want to focus on the function sine of x for the x values that are between 0 and 2 pi. So that's just talking about, we can look at this from a couple of different ways. Just remember, we know that sine of x is going to look like this. And we also know that 0 to 2 pi, graphically, 0 to 2 pi, or if we think in terms of our circle, that's one rotation. Okay. We need to start just like we did before. Let's find the derivative. All right, what is the derivative of sine of x? Well, the derivative of sine, remember, is simply cosine of x. What did we do once we had the derivative? We wanted to find the critical values, so set the derivative equal to 0. And let's find the angle measure, or the angle measures, that has a cosine value of 0. So that would be here here, and here, which corresponds to, you know what? Okay, hold on. I'm not looking at this graph. This graph looks at that one. So cosine, let's think about this. 1, 0, 0, 1, negative 1, 0, 0, negative 1. So what values of, what angle measures have a cosine value of 0? That would be pi over 2 and 3 pi over 2. Okay, so these are critical values. So if you recall, what did we do with our critical values? We took those critical values and we put them on we created a little sign chart, and 3 pi over 2. Now let's talk about this. I want to know, what I want to find is information about the derivative. I want to know where is the derivative positive and where is the derivative negative. And I know that that's going to be on these three intervals. Pi over 2 and 3 pi over 2 are the critical values, which means that's where the derivative may or may not change signs, but it still gives us information. So, how do I know, without really thinking about the graph of what cosine looks like, how do I know if the y values are positive between 0 and pi over 2 and 3 pi over 2, and 3 pi over 2 to 2 pi? Well, let's test some values. Let's think about an angle that is less than pi over 2, such as pi over 4. So let's test pi over 4 and substitute that into the derivative. So right here, cosine of pi over 4 is in quadrant 1, and I don't really care about the value. All I care about is the value of cosine of pi over 4, positive or negative. Well, it's in quadrant 1, so that will be positive. So from 0 to pi over 2, cosine is positive. From pi over 2 to 3 pi over 2, let's test a value. So what would be a good value to test between pi over 2 and 3 pi over 2? How about pi? Well, cosine of pi, again, I don't really care about the value. I just want to know, is the sign of cosine of pi over 2 positive or negative? And that's negative. And between pi over 2 and 3 pi over 2, cosine is negative. And then an angle that is greater than 3 pi over 2, how about let's use another angle in the pi over 4 family, and that would be 7 pi over 4. So what is cosine of 7 pi over 4? Well, in quadrant 4, 7 pi over 4, cosine is positive. All right, so the derivative cosine is positive from 0 to pi over 2. The derivative cosine is negative from pi over 2 to 3 pi over 2. And the derivative is positive from 3 pi over 2 to 2 pi. And I'm just stopping it at 2 pi. So what kind of information does that give us? Well, about the original function. Well, I know that the original function will increase from 0 to 2 pi. 0 to pi over 2. I know that the original function will decrease from pi over 2 to 3 pi over 2. And from 3 pi over 2 to 2 pi, the original function will increase. I also know that at pi over 2, the original function will have a maximum. I also know that at 3 pi over 2, the original function will have a minimum because the derivative is changing from negative to positive. Okay, so let's identify some things. So let's identify the maximum and minimum. So that means I'm going to substitute pi over 2 into the original function. So f of pi over 2 will equal the sine of pi over 2, and the sine of pi over 2 is 1. So I have a maximum at pi over 2, 1. Okay, I also will substitute 3 pi over 2 into the original function. Sine of 3 pi over 2, which is negative 1. So 3 pi over 2, negative 1, is going to be a minimum of the original function. Okay, and again, how did I come up with this? Well, I found the x values where the original function would have a maximum or a minimum by using the derivative. Wherever the derivative changes from positive to negative, the original function will have a maximum. And wherever the derivative changes from negative to positive, the original function will have a minimum. So once I found those x values, substitute those two x values into the original function, and you will actually have the point where the maximum and the minimum occur. So let's go ahead and identify a couple of things in our list. We found the critical values. We haven't found the hypercritical value yet, but I want to go ahead and find, or at least identify, that f increases f is increasing on 0 to pi over 2. Now again, why am I starting with 0 instead of negative infinity? Well, because in the beginning, I wanted us just to focus on the interval from 0 to 2 pi. So f increases on 0 to pi over 2. F also increases on the interval 3 pi over 2 to 2 pi, because f prime is greater than 0. F decreases, or is decreasing, on the interval pi over 2 to 3 pi over 2, because f prime is less than 0. Excuse me. So wherever f prime is greater than 0, your original function will increase. Wherever f prime is less than 0 or negative, the original function will decrease. Okay, we also have found that f has a local maximum at the point pi over 2, 1, and f has a local minimum at the point 3 pi over 2, negative 1. Okay, now we want to find some information about concavity and a point of inflection, and that comes from a second derivative. So my second derivative, let me get that out of the way. My second derivative is equal. Now, what's the derivative of cosine? Well, that's negative sine of x. If I need to find points of inflection and concavity, I need to find hypercritical values. So I have to set the second derivative equal to 0. And I now want to identify the values, or the angle measures whose sine values are equal to 0. So if we look back at our little angles here, then sine will be 0 at 0, pi, and 2 pi. So x equals 0, pi, and 2 pi. So if I create my sine chart, then I will put 0, pi, and 2 pi. Now, I don't really need anything that's less than 0 because I only want to focus on the interval from 0 to 2 pi. So I don't need this interval, pardon me, and I don't need this interval. So what I need to do is I want to now figure out, is from 0 to pi, is the derivative positive or negative? So I'm going to test a value. I'm going to test, give me an angle. Let's think about an angle that's between 0 and pi. How about pi over 2? Okay, now we go back up here to determine if the derivative, negative sine of x, is positive or negative at pi over 2. So I have negative. What is the sine of pi over 2? Well, the sine of pi over 2 is 1. The negative out front makes it negative. So the second derivative between 0 and pi is negative. That means the graph of the second derivative is below the x-axis. Now let's pick a value between pi and 2 pi. Well, how about 3 pi over 2? I'm sorry, I'm just writing everywhere. It's a little cleaner on the notes that I've provided. But if I want to test 3 pi over 2, what is, oops, let me squeeze that on there. So what is sine of 3 pi over 2? That's negative 1, and the opposite of that will be positive 1. So between pi and 2 pi, the second derivative, if I were to look at the graph of the second derivative's graph would be below the x-axis from pi to 2 pi. Okay, so what does that tell us? Well, from 0 to pi, the original graph is going to be concave down. From pi to 2 pi, the original graph, the original function's graph, will be concave up. And at x equals pi, we will have a point of inflection. So let's talk about, I'm going to scoot this up just a little. Let's talk about a point of inflection. I need to evaluate the original function at pi. So sine of pi is 0. And so that means that the original function, f, has a point, I'm just going to say pi, at pi comma 0. And I know from 0 to pi, is the original function is concave down, so f is concave down on the interval 0 to pi because f double prime is less than 0 and f is going to be concave up on pi to 2 pi because f double prime is greater than 0. Pardon me. Okay, so let's just take that information. I'm going to scoot this up as best I can. And if I really just wanted to take this information to sketch the graph, here's the y-axis, here's the x-axis. I'm going from 0 to 2 pi. And so I want to graph the maximum. So I have a maximum at pi over 2, 1. And if I label my graph like I would in pre-calculus, I would have pi over 2, pi, 3 pi over 2, and 2 pi. So at pi over 2, I have a point at 1, which means this local maximum is going to have to change directions from increasing to decreasing. I have a local minimum at 3 pi over 2, negative 1. And because it's a local minimum, the graph will change from decreasing to increasing. I have a point of inflection at pi 0. So right here is the point where the graph of sine of x is going to change concavity. So this particular function, sine of x, increases from 0 to pi over 2, which makes sense. This function decreases from pi over 2 to 3 pi over 2, so makes sense. So now it does this. Then from 3 pi over 2 to 2 pi, it increases, the graph increases again. So you'll notice that f increases on 0 to pi and 3 pi over 2. So right here, and 3 pi over 2 to 2 pi, so it increases. You'll notice that the function decreases between the two. You'll notice that f has this point of inflection, which means the graph of the original function is going to change concavity, and we know that f is concave down on 0 to pi, which it is, and concave up from 0 to 2 pi. So if this particular function, we knew what the graph would look like. We used the first and second derivative to actually help us graph this function. And by looking at this, I think we can tell where this does look exactly like what we would have thought the graph should look like. Not all graphs and not all functions, the graphs are not necessarily something that we recognize or know. Okay, so I'm going to stop this video now, and I'm going to create another one that will, I think, work through the last two examples, and then at that point you'll be able to work on your lessons or your assignments.